In today's class, we will start with the nonlinear Raman effect. So, in this nonlinear Raman effect, this is not that much risky or difficult topics. There are few simple concepts in Raman effect. Okay. So, in nonlinear Raman effect, what actually nonlinear. So, this will start with a very high intense laser pulse. So if you consider the basics of the polarization, okay, for example, if you consider the linear polarization cases, linear polarization. So I will be going through some of the important points. You can read the textbook for more details and other references. So if you consider the linear polarization, okay, this is nothing but your polarization is directly proportional to the applied electric. Okay. And now if you consider a very high intense field, which means that your electric field is very large or very high, okay, which means that your intensity of your laser pulse is very high. In that case, uh, this okay, I will write this as alpha. This, this is E will be equal to alpha times E, where alpha is the polarizability. So this is the linear polarization. But when you use very intense laser beam, a giant laser beam we are considering, in that case, what will happen? So when very intense means that pulse with the high intensity, pulse with high intensity. If we consider this case, then this polarization become nonlinear. So then you have to write your polarization as B equal to alpha E, sorry, yes, alpha E plus, then you will be having some additional terms square plus half into gamma EQ plus. And this beta, gamma, etc., they are called as hyperpolarizability tensor. So in that case, we are considering the polarizability as a tensor form. Then your electric field is very high. So beta is, you can call this as hyperpolarizability tensor. when the intensity is very high, this alpha is no longer a constant. Instead of that, it will become a tensor. Okay? So in different direction, we have to consider it differently. So we have alpha here, beta, gamma, everything. So alpha is polarizability. Okay. Then we have beta, which is hyperpolarizability tensor. Then we have gamma, which is the second hyperpolarizability tensor, and so on. Okay. And other terms also have to consider depending on which kind of phenomena we are going to see. So these values depends on the electric field configuration, so electrons configuration or molecules that we are studying. Value of this coefficient that will be depending on the configuration of the sample that you are studying. And this P now we can also replace this alpha E of beta E square, all those things with the susceptibility, that chi term. So with that, we can write this as P equal to chi E plus chi E square. So here it is chi 3 chi 2 plus x. So this is also a conventional method of representing the same equation. Okay. So this is the same equation we have here. So it is a conventional method, and we have this as your polarizability. Then we have this these things which are having higher order electric field, that is E square, E cube, etc. Along with that, these functions are coming chi2, chi3, chi4, etc. And these are called as nonlinear terms, nonlinear polarization. So this is due to nonlinear polarization, or I can write it as I can write it simply chi2, chi3, chi4, etc. are nonlinear polarization. And there are many properties will depends on these coefficients, constants. For example, if your system is having center of symmetry, then you cannot expect this that system. You will be having only those odd terms for system or sample with center of symmetry, molecule with center of symmetry. So such kind of properties will depends on these values, but we are not going to look into all those details. But this is just a just general study of Raman effect. So we will not go into the deep how it is going to come and all. So anyway, the basic is that when the electric field intensity or the pulse intensity is very large, then your polarization will become nonlinear, so that it will affect your Raman scattering also. So in this case, in this scenario, we have two different Raman effect to discuss mainly. Under this, we have a inverse Raman scattering also, so that we will discuss in the next class. So today we will be discussing on two different nonlinear Raman scattering phenomena. One is hyper Raman effect, hyper Raman effect. So I will be discussing the very basic of all these effects. So you must read the textbook to have a complete picture of this. So when we have a very high intense pulse, all these nonlinear phenomena will happen when we are having very high intense pulse. So when we have very high intense pulse, okay, so the captured radiation consists of u0, u0 plus mu, 0 minus mu. So when you are using very high intense pulse, so this is a normal Raman scattering. You will be having that fundamental line mu0, which is Rayleigh scattering, and then you will be having mu0 plus mu m, that is corresponding to anti-Stokes line. Then you have mu0 minus mu m, which is for Stokes line. And along with this, we will be having, when your intensity is very high, we will be having some other frequencies also, like 2 mu0, then 2 mu0 plus mu m, then 2 mu0 minus. And this particular phenomena is called as hyper-Raman effect. And this we can, so this is the Rayleigh line, Rayleigh scattering or Rayleigh line. And these two are uh, normal Raman, normal Raman Stokes and anti-Stokes line. And this is 2 mu 0. This 2 mu 0 is the hyper Rayleigh scattering. Rayleigh line or Rayleigh scattering, and this one is these two are hyper Raman Stokes and anti-Stokes line, anti-Stokes line. So this is the basic idea behind this hyper Raman effect. When your intensity of the pulse from your laser source is very high, then in addition to the normal Raman effect, we will be having some more bands in the spectrum, some more lines in the spectrum, and that particular effect, which is called as, and it will be like this. It is called as hyper Raman. This can be explained in the simplest way by quantum theory explanation. So in this, we will be considering the different energy levels. For example, let's consider different energy levels. Let's say there are 4 energy levels in here, and the last one is this one is ground. So let us, and then you have some virtual lines, virtual levels here, virtual energy levels. That virtual energy level. So suppose there is a transition happen, because when you are having that H0 radiation which is coming and interacting with that molecule will be in the ground state, and from the ground state it will go to the excited state. Okay, like this, going to this excited state. Now, if suppose when it is let's say this another H0, so this H0 will be used by the molecule, and when it reaches at this point, the second photon comes and interacts with this molecule, and that uh, energy also absorbed by the molecule, and it will again go to the next level. Next level after absorbing the second quanta of energy, that is second h nu 0. Okay. So these energy levels are h nu 0, and with the first photon absorption, it reaches at this first virtual energy level, and if after that, it will absorb the second photon with the energy h nu 0, and it will go to the next excited uh, virtual energy level. And from there, it will come back. From there, to this level, to the ground state. Okay. When it comes to the ground state, then it will be releasing uh, 2h nu 0 energy that will be coming. So this 2h nu 0 energy, it is not normal, because you cannot observe that when your intensity of your laser beam is small. This cannot be. This particular process will not happen. Why it is not happening? If you're going into detail, there are a lot of physics behind these processes. Suppose if you have a molecule here, let's say, a very simple manner for understanding. So suppose we have one molecule here, and a photon is coming and interacting with this particular molecule. Okay. So then that molecule will go to the excited state energy level, which means that not the entire molecule which is going, one particular frequency of vibration or rotation motion will be absorbing that particular photon energy. Okay, and that will be using for that uh, vibration of that particular molecular band or molecular that bone. Otherwise, it will be used by that particular portion of the molecule to rotate. Okay. So all those things are possible. But in energy level representation, we just say that the molecule is excited, which means that the molecule is absorbed that radiation and used for some vibrations or rotations. Okay, so when one photon comes and interact with this particular molecule, so it can be absorbed by any of those vibration or rotational motions or associated branches of this molecule, and it will go to the excited state. If your intensity is low, which means that the interaction of number of photons with the sample will be less. Okay. So if you are having one photon which is coming in 1 second, for example, that is not that much possible. But anyway, so let's just consider that only one photon is coming and interacting with the sample. Then it can be absorbed by the sample, and some vibrations may happen. And when then it will go to this particular level. Okay. So suppose this two level, uh, this higher excited level, suppose it is having some 10 raised to minus 10 seconds of lifetime, or 10 raised to minus 20 seconds of lifetime, for example. So it will be going and coming back, okay, to this ground state and coming back. So when you are having the first photon which is interacting with this sample, and this photon will be absorbed by that sample, and which will go to the excited state and come back. And the second photon should interact with the sample within this time frame. Okay, then only it will go to the next energy. Okay. So if you do not have enough photons, if number of photons are less, the second photon may not reach at the same time when this molecule at this position, the excited state. So which means that the molecule will not be interacting with the photons. That interaction if you are considering that interaction ratio or interaction rate of the molecule and photon, it will be larger when you are having large number of photons. If you are having large number of photons, then the molecule will interact much larger as compared to the previous case, or you are having less intense pulse. High intense pulse means number of photons are higher, so this number of photons may interact these molecules in the higher energy level also. So that will give you this exciter, the second exciter. Otherwise, if you are using low intense pulse, then this phenomenon. Okay, so this 2 nu 0 is can be observed when your intensity of the pulse is large enough. Okay, and this particular frequency is we called as hyper Rayleigh scattering or hyper Rayleigh. And the second case is that this same molecule which is going to this energy level, same molecule is going to this energy level. Okay. And when it come back so when it comes back, let's say it is reaching somewhere here. Okay, and in that case, we'll be having this is absorbing 2 photons and it is reaching in this excited level. Okay, so this process and their process will take 2 h nu 0 energy. So when it come back, it will be having an energy of h nu 0 minus mu, and this mu is the energy separation between this energy. So if you consider the energy separation between this energy levels as mu, then you have 2 h nu 0 minus mu is the radiation which will be emitted. Okay, so the frequency or the energy is reduced, and which is corresponding to the stop line. Okay, and in the third case we have to consider it is the molecule exciting from somewhere here, which means that it is already in that excited state. So that will be going to this level and again interacting with one more photon and going to the next energy level, next is higher energy level. And when it come back to this stage, it is going to reach at the ground state. And in this time we have same energy. Then we have here in this so there may be slight variation here because we are starting from here and it is observing some. So it will give you some h nu 0 plus mu m as the output frequency, 0 plus mu m, because it is reaching at the ground state. So at the output we will be having a radiation of h nu 0 plus mu m, and this is 2h nu 0 hyper. This is hyper Raman Stockand, hyper Raman anti-Stockand. Hyper Raman effect. So this is 2 mu h nu 0 plus mu, and this is corresponding to the anti-Stoke line because frequency has increased. And since it is going from the higher state, higher energy, not from the ground state, so the number of molecules in the higher state or excited state will be less. Okay, so that the intensity will be less corresponding. Okay, so this is the these are the 3 different phenomena. This one is hyper Rayleigh line. Hyper Rayleigh line. This one is hyper Raman Stokes line. And here it is hyper Raman anti-Stokes line. Now there is another method, another important nonlinear effect or nonlinear Raman effect is the stimulated Raman scattering. Stimulated Raman scattering, SRS. Stimulated Raman. So in this case also we need very high intense pulse. So we use a very giant laser pulse. Okay. So if a giant laser pulse, laser pulse is used as the incident radiation of light. Scattered radiation will be scattered radiation is observed so you can write this as when a giant laser pulse is used as the incident radiation. Scattered radiation is observed with the fundamental line and Stokes anti-Stokes. So this radiation, the scattered radiation is observed. Here you can add one more that along the laser direction, okay. So you can include it in bracket. So that you will be observing these shocks and anti-shocks lines along the laser line as well as it will shifted from that position. So it means to this laser direction. Okay. So we have this fundamental line and many shocks and anti-shocks lines. And this phenomena is known as stimulated Raman. And what is the importance of this stimulated Raman scattering? So in normal scattering, what will be the condition if you are having some h nu 0 energy is interacting with the I will use these top lines to explain this. Okay. The similar behavior we can observe with the anti-stop line also. Suppose you have this much energy levels. This is the ground state energy level. This is excited state. This one is also excited. Virtual excited. So when you have one h nu 0 incident radiation, which this is a in this case of a normal case, normal Raman phenomena, Raman effect. we have this kind of excitation from the ground state, and it will be coming back to the this higher energy level. And in this case, we will be having a radiation which is equal to is having energy h mu 0 minus m, and mu m is the separation between the two energies. So this is nothing but the Stokes line which is coming out from the sample. This is the spontaneous Raman scattering, or in the normal Raman scattering. You can say this is spontaneous scattering. Okay, but this is spontaneous Raman scattering or normal Raman scattering. But in the case of stimulated Raman scattering, what will happen if you are having uh, the same kind of energy levels from state and the state? So this incident radiation is coming, interacting with this molecule. Okay, so we'll be having this excitation, and same phenomena will happen here also. We'll be getting h mu 0. But in this case, for example, many such radiations are coming. Okay, h mu 0, for example. So here what will happen, h mu 0 minus mu m. Many such radiations are coming. So the intensity of this particular line will be getting increased. So at the output, we will be having more number of such lines, or the photons with that much of energy will get in this particular process. Okay. So if there are n h nu 0 n such photons which are coming along with this h nu 0, along with this also h nu 0 minus mu m also will be interacting with material. So in normal cases, it will not be having enough intensity. The photon number of photons will be less in this case. But in this case, if you are having more number of such photons, h nu 0 minus nu m, because already you are having very high intense pulse, number of photons are very large. So if you are having more number of this photons that are present in your in process, h mu 0 with energy h mu 0 minus, and that will be getting amplified or gain. It will be gaining same frequency with the fraction of this h mu 0 with the material, so that the total number of photons with this much of energy h mu 0 minus mu, that will be getting increased, and this will become very high intense. This particular beam will become very high intense, and that itself will produce the scatter. So this h nu 0 minus nu m will go and interact with the material, and it itself will produce the next scattered beam. So in that case, we'll be getting a radiation which is less than that. So in this case itself, you can see if you are having these two h nu 0 minus nu m energy photons, and you have h nu 0, a photon with h nu 0 energy. So when it comes out, you will be getting 3 photons with h nu 0 minus mu m. So large number of photons with h nu 0 interacting with the material, because you are using very high intense pulse, so that you will be getting very large number of h nu 0 minus mu m photons, and that photons will be having very high intensity in this case, and that will cause the next scattering. So instead of this line which we are going to give through lasers, instead of that, this scattered light itself will be sufficient to produce the next scattering in this material, because they are very high intensity. Okay, so then we will get the additional lines along with this particular h mu 0 minus. So actually, so in this case, I don't think I have to explain. I have to write all those things here. So we will get a different frequencies. For example, in the first case, you are getting this one, it's nu 0 minus nu m as your energy of the photon. Okay, and you will be having if you are already having n this much of n number of photons with this energy, you will be getting n plus 1 photons of energy with this much of frequency or energy. N plus 1 photons of this much of energy h nu 0 minus nu m. And all this, suppose this is the first case, okay, and you get a scattered beam, that is the stock line, and these stock lines are now these stock lines are very much intense, unlike the conventional Raman spectra, and that will be enough to produce scattering in the sample, and that will produce h nu 0 minus 2 nu m. So the next radiation, which means that this radiation interact with the material or the sample, and will excite the sample to some energy level, and when it come back, it can produce some other scattering form, like mu0 minus 2m or mu0 plus 2m, like that. Okay? So this high intense field itself is enough to produce the scattering, and we will get additional scattered beam or spectral bands. Okay, so I will just point it out here. So this process continues. Okay, so this is not going to stop here. So this process continues, then this number of photons will be larger, but each time the intensity will be getting reduced, so that the number of interaction with the sample will be getting reduced, and the intensity will get reduced each time, but still it will be having enough intensity to make this scattering, and it will be observable, and it will again produce that premium, all those lines, particular phenomenon. Okay. So the scattered radiation, I will just point it out here. So the scattered radiation is the scattered radiation is amplified, as you can see from here, amplified, and mechanism mechanism responsible mechanism mechanism responsible for this is enhancement. This mechanism responsible for this amplification of the scattered beam is the enhancement of Raman stroke amplification. Enhancement of a mechanism behind this process is the enhancement of Raman stroke amplification. Okay, so the line u0 minus mu m is very intense. Is very important point. That intensity of the light high. So the mu0 minus mu m is very intense, and which can produce mu0 minus 2 mu m frequency. And this process continues. Okay, this process is known as stimulated Raman. So what is the difference between these two, normal Raman scattering and simulated one? Here we will be having this incident radiation interacting with material and giving that anti-stoke and stoke lines. And next time also the same radiation has to interact with this material and give the same anti-stoke and stoke line. But here the difference is that when you are having very high intense pulse, and first you will be getting anti-stoke and stoke line because of this one, it's nu zero. Along with that, this H nu zero nu m also will be much intense and produce these lines like H nu zero minus 2n and all those things. And this is getting very high intensity because of some stimulated emission. As you can see from the laser principle, you have that stimulated emission of radiation. Like that, you will be having very high intense pulse or radiation with the energy of H nu zero minus nu. Here, unlike in this case, we will be having that intensity will be less. But here, since the number of photons already which is interacting with the material is very high, and we have number of such photons with H nu zero minus nu m, and that will also produce or generate the next line. Like in this case, it is H nu zero minus nu m. That photons will generate with radiation with H nu. Okay, so it is like a stimulated or stimulating process is happening in this Raman scattering. So this is that's why it is called as stimulated Raman scattering. Okay. So this further can be if see that process, then suppose if you are having this, so this we can treat it like this. You're having this excited level, and this is your ground state. So if you are having an H nu zero minus nu m energy which is incident on that particular sample, so that the sample will go to some excited energy level and come back to this excited energy level to the ground state, so that you will get H nu zero minus 2 mu. So this will be like initially you'll be having suppose here. The next time, so it is going from here, right? Mu zero plus. So I will get, okay, this is also okay. But, don't get confused because it is just a representation. So it is so this energy level difference, this energy level difference. Okay, but after absorbing this energy, H nu zero minus mu, the sample will go to the excited state. So it does not mean that the sample is going there, but it is just absorbing energy and some vibration or rotation is happening. So in that case, it is going to that excited state and coming back to some other excited near to that state energy level. So here the lifetime will be very small here. So this will be H nu zero minus 2 nu m. It will be releasing some radiation with the energy which is equal to times nu zero minus. And if you are having a large number of such photons in your system, then it will produce, for example, if you are having n such photons here, nh nu zero minus, then you will be having this n plus 1 times of this. Along with that, the interaction with that, we have the conventional Raman scattering also. So which means that the lines which will be produced by the Raman stimulated Raman scattering will be very intense. Okay, so it is similar to that laser action. If you are using this, that is the basic principle of the laser light amplification by stimulated emissions. Same process will happen here. That intensity of the lines will be very high as compared to the spontaneous Raman scattering. So in this case, we have n number of these h nu 0 minus nu m energy photons are coming and interacting with sample. You will get n plus, in this case, you will be getting plus one number of this. And this one is coming from that h nu 0, which is interacting with the sample, which will also produce h nu 0 minus 2 because of the conventional Raman scan. Okay, so this is the process that will be happening in this kind of simulator Raman scattering phenomena. And from this, you can easily observe that number of photons will be getting increased, and hence the intensity of the stroke and anti-stroke will be very intense. This particular, if you are using that high intense pulse. Okay. And this is another nonlinear phenomena that you can observe. And in this case, we will normally use a source which will be a ruby laser. So this should be a giant pulse. So the intensity should be very high. So giant pulse ruby laser. So from this laser, we'll be getting that very high intense pulse. Okay. So it will be going like this, and it is focused by a lens to the sample. Can use nitrobenzene as your sample, and then it is directly selected photography. This is the second nonlinear Raman. So when you observe this, this is a three-dimensional figure. Okay, so this will be a three-dimensional propagation of these radiations and focusing those things, and this will give you a circular pattern. So if you observe that circular pattern, then you will get the like this photographic film or plate. At the center, will be having very dark. So if you are using this plus benzene, you will get center very dark red spot, a very dark red, which means that very high spot here. And then we have this first circle, this so or let me see how it is. So this is very thick. First one is very dark red color. Okay. Then we have this like okay. So that is the first one. Some higher. And then we'll be having next line, and next one will be, I think, this orange color. Okay, so some like that. Let's consider this as, so the second line will be be having less indents. It will be like this. So this kind of figure you can get. And the central one from this lines, the central one is this one which is very dark dark red color. So this one is nothing but the laser beam itself. This is because of the ruby laser output one, and the stock stocks line. Okay. Why this is coming at the center? Because they are going at the same direction of the laser pulse. Okay. So this is because which are same direction along. So at the center, we will get a very dark red spot that is that corresponds to the ruby laser output. That laser beam itself, that is nothing but the same frequency which is coming. And the also the Stokes lines also included in that, okay, that spot, because the Stokes lines will be having less frequency than that, so it will not be shifted to output. So it will also be there because both of these lines will be in that laser direction. Yeah, same direction of the laser. And the second we can see a lot of rings around this dark spot, and these rings are anti-Stokes lines. Okay, so these are the anti-Stokes lines. Okay, these rings which are uh, all these are anti-Stokes lines. These Stokes. Okay. And these anti-Stokes lines are actually it is deviated from that central position. Slightly deviated. That's why it is coming like this. So this anti-Stokes line, as you can observe that the first anti-Stokes line with the red color, which is much high index. Okay, so it is higher index, not much high index than the central one. Central one is the highest one. And but comparing to the normal Raman scattering, this anti-Stokes line itself, we know that the anti-Stokes lines will be less intense in conventional Raman scattering processes. But here we can see that these anti-Stokes lines are much higher in their intensity. Intensity is much higher. And the remaining anti-Stokes line, when you consider this orange one, then yellow, then green, the intensity will get reduced. The intensity is getting reduced each time. Okay. So these high intensity Raman lines or the anti-Stokes lines, that lines itself it can be used as a laser source. Okay. So in conventional Raman spectroscopy, the intensity of the Raman lines are very small, even though the Stokes lines are more intense than anti-Stokes lines. But these are in normal cases, these may not be observable itself. Okay. We have to use some particular technique to observe those lines which are coming after scattering. So it's which are very weak. Okay. But in this stimulated Raman scattering, since there is a stimulation process which is happening and number of photons which are much larger than the conventional Raman scattering process, because of these lines which are produced by these stimulated Raman scattering, whether it is the top line or anti-Stokes, they are very intense, much intense. So these intense lines we can use. So in this case, we will get very bright lines, stroke lines and anti-stroke lines. So this SRS phenomena, by using this SRS phenomena, we can choose some suitable materials, and from that materials we can produce these different stroke lines or anti-stroke lines, so that we can use these lines as a laser source. So by using this SRS phenomena to generate number of indents and coherent laser beam. Or you can write the SRS phenomena to, instead of generate, you can write to make number of indents and coherent laser sources. That is also okay. So that is the basic difference between the conventional and simulated Raman scattering processes. One is linear phenomena, another one is nonlinear phenomena, and in the SRS or simulated Raman scattering, we'll be having very high indents lines. So even if you are considering this particular case itself, you are sending this very red color, deep red color or dark red color ruby laser you are using, but you are getting another red frequency, okay, and another orange color, which means that you are getting some other frequency, and then yellow color. All these lines are very intense, and all these lines can be used as different laser sources with a different wavelength. Okay. So that is possible by using this simulated Raman scan. And another possibility is that by mixing of two frequencies, simulated Raman scattering, SRS can also be achieved. Means that the simulated Raman scattering can be achieved by another method, which is achieved by mixing of two lasers or laser frequencies. Let's say mu1 and mu2. So this is also possible, and in this case, mu1 should be greater than mu2. You can take in anywhere, conventional manner, that mu1 is greater than mu2, let's say, and so mu2 stimulate the scattering. Mu2 stimulate the scattering, and at mu2 equal to mu1 minus. So at this point, you will be having mu2, which will be stimulated. So in this process, what is happening? This process mu2 will be gaining. mu2 will be. I will explain that what is this totally. Okay, so this is why it is this process. If you are using that mu2 gain in your spectroscopy, then it is called as Raman gain spectroscopy. Raman gain spectroscopy. Or if you are considering the loss of mu1, then we call it as Raman loss spectroscopy. Raman loss. It depends on which one you are using. You are measuring that loss, or you are getting that measuring that gain of mu. Depending on that, you will be having Raman gain spectroscopy or Raman loss spectroscopy. So with respect to this, we'll be having Raman gain and Raman loss spectroscopy. Okay, so this is also possible. So basically, it depends if you are having. I will show that how it is happening. If you are having mu1 and mu2 as your frequencies, and in this case also mu along with the mu2, what will happen to mu1? Mu1 will be annihilated. Means that its intensity will get reduced. That frequency will be getting because when you're that what that means is that you'll be having energy levels like this, and you're having h mu1 energy in between this ground state and this excited state energy. So when it is going with that energy h mu1, so the sample is going to take this h mu1 and excited to this energy level. When it comes back, it will be giving you, let's say this is mu1, so it will be giving you s times mu1 s mu1, and this should be equal to that h mu2. So this mu2 frequency should have all the properties of h mu1 minus. Okay? And in that case, if you are having this kind of a process, this is going to happen, then obviously this mu1 frequency will be annihilated, and mu2 will be always gained, will be increased. Okay? So this one will be having some kind of a stimulation in here. So mu2 will be stimulated in this scattering process. This mu2 frequency will be stimulated. By this means also we can generate that stimulated Raman scattering by using two different frequencies. By this way also we can. So as you know, this Raman scattering is an inelastic scattering of photons by the molecules in the sample. Okay, so the scattered photon, in case of Raman scattering, the scattered photon has energy which is equal to h nu 0 plus some nu m, or h nu 0 minus nu m. That depends on whether the scattered radiation is stock line or anti-stock line. So depending on that, we'll be having difference in frequency. Okay. So we have in normal Raman scattering, if you consider normal Raman scattering, this is an inelastic scattering. So you know that inelastic scattering. Why it is inelastic? Because some energy is transferred to the molecule, or some energy is taken away from the molecule. So in this case, when the radiation comes and hit the sample, when it comes out of the sample, it can have a frequency which is less than the incident frequency. It can also have a frequency which is higher than that of the incident frequency, or it will be having the same frequency. So there are different possibilities for the case of a normal or conventional Raman scattering. Because it's an inelastic scattering, some energy will be lost in some case, some energy will be gained in some case. So those energy will be this radiation will be having same radiation, same uh, frequency as the incident radiation. For example, it's nu 0. Okay, and this one will be having its nu 0 plus some nu m, and this is the total energy. Okay. And here we will be having h nu 0 minus nu m of this radiation. So we will be having three different lines. or bands we'll be getting at the output of after scattering. Okay, so these are, we already know this is the anti-stop line. This is the stop line which is having frequency less than the incident frequency. And here we have the frequency which is higher than the incident frequency. So this is the normal Raman scattering, which is an inelastic scattering. So if you are having this anti-stop line, if you are having this anti-stop line, then the molecule of the sample are given this energy to the photon. Okay, so that the photon's energy increases, which means that its frequency will get increased. Energy increasing means frequency get increased. Okay. Similarly, if the intensity is going to increase, then the number of photons will be getting increased. So here the energy is increased because some of the energy provided by the sample to the photons, so that the frequency is changed to its nu plus nu m. Initially, it was having nu zero, so that frequency is changed to nu zero plus nu m, so that the energy of the photon get increased and the frequency, because of that, it will be shifted to higher frequency range of the spectrum. And there are some of the spectral line, or almost most of these spectra or the incident radiation will be coming as such as the incident radiation frequency, same frequency as the incident frequency. That is the Rayleigh scattering. And the third one is h nu 0 minus nu m, which is the Stokes lines, where you have the, the energy which is given by the photon to the molecule. Okay, so that the photon energy will be decreased by an amount of h nu m. Okay, so that the total energy will be h nu 0 minus nu. So this is the scenario of the Raman, or the inverse of this. So if this process is inverted, then phenomena anti-stock Raman line, is H nu zero radiation, as we discussed, and which will be interacting with the molecule, and the molecule will give some energy to the photon, so that initially the molecule will be at some higher energy level. Let's say this is E2 and this is E1, and this molecule will come to the ground state or some lower energy level with release of frequency nu m, or the that energy will be transferred to this photon, so that you will be getting an additional energy h nu m here. Okay. So that will give you the output here. The output will be h into mu 0 plus mu. So this is the normal or the conventional Raman scattering process for the anti-Stokes line. Now, if you consider the inverse anti-Stokes Raman effect or Raman scattering, if you consider inverse anti-Stokes anti-Stokes Raman scattering, if you consider, now what will happen? Just the inverse of this will happen, or inverted form of this will happen. So in this case, input will be on this side. So we can write input here, and the input will be h nu 0. Then input will be h nu 0. Here it will be h nu 0. H times nu 0 plus nu m. So this is the input radiation, which is going to towards that sample and interact with the sample, and that input, which will give you, you are sending input of radiation h nu 0 plus nu m. That will be given to the sample, and the sample is initially at the ground state, for example, or the lower state. Then it will go to the excited state. Okay, and with that, so the sample will absorb some of the energy from the incident radiation, which is equal to the frequency nu m. Okay, so that here we will be having h nu m, which is absorbed by the sample, the energy which is absorbed by the sample to go in order to go to the excited state, in order to jump to the excited state or excited energy level. And along with this h nu m, we have the h nu 0. Okay, and this h nu 0 will be the output. So now your output is h nu 0. So it is just an opposite action of the normal or the conventional Raman scattering process. So here what will happen, you are giving h nu 0 energy, or h nu 0 plus nu m energy uh, radiation to the sample, and the sample absorb this radiation. Sample will interact with its radiation and scattering happens. And because of that scattering, it will absorb some portion of that radiation, and it will go to the excited energy level. And the radiation which is coming out from the sample will be having h nu 0 energy. And this process is called as the inverse anti-Stoke Raman scattering. Similarly, we can say about the inverse Stoke Raman scattering also. So in that case, what will happen? We have instead of here we will be having h nu 0 minus nu m as your incident radiation, and you'll get some energy from the sample, and you will be getting, as a result, you will be getting h nu 0 as your output. And that is the inverse Stoke Raman scattering. So in that case, you have to give. So in the case of Stoke, inverse Stoke, consider inverse Stoke Raman scattering. We fill this. So in that case, what will happen, instead of here, we have h nu 0 minus nu m in the input side, and that will be given to the sample. Okay, so it will be uh, that result in a decreasing of the energy of the scattering molecule by h nu m. Okay, so in that case, we'll be having, here we'll be having, I think I don't have to draw that figure. So you'll just get here. Here you will get plus h nu m, or this one will be minus h nu m we are having. So this will be splitted into and h nu 0. So this h nu m, that will be gone when it. So you can write this as your output, and plus 7 h nu m. Okay, so you can write this, or it will be just gone from here. It will be 0, because you are getting some radiation from the sample. Okay, so this when the sample comes down from the higher energy level to the lower energy level, it will release some h nu m energy, Okay, that energy you have to add with this incident radiation. So it's nu zero minus mu m plus mu m will come. So that minus mu m and plus mu m get cancelled, and you will get nu zero as your. Okay. But here we have this h nu m which is used to uh, go from this ground state to the excited state by the sample. So here an additional h nu m will be given by the sample, and the resultant will be having 0. Or you can write it as also write this as here we'll be having h nu m and plus h nu m here, and this plus h nu m is coming from this sample when it is coming down to the ground state or the lower state. So this will be cancelling each other, which means that you are sending a radiation which is having energy which is less than h nu 0. You can see from here, which is having energy which is less than h nu 0. So an additional energy of h nu m will be given to the photon, so that it will gain some energy and it will become having energy of h nu 0. So that is the inverse stock uh, Raman scattering. Basically, you are getting this frequency from a lower frequency, or you are getting this higher energy from a lower energy. In the case of inverse stock Raman scattering, otherwise you will be in conventional Raman scattering, or where you will be getting an energy which is less than that of the incident radiation. Okay, but in this case, we are getting an energy is greater than that of. So in stock Raman scattering, normal Raman scattering, you are providing some energy, and you are getting energy which is less than that what you have provided. And here we have given some energy which is less than the output of whatever you are getting at the output. So that is just inverse of the normal Raman scattering. In the same way, we can have a in anti-stock inverse anti-stock Raman scattering. In conventional Raman scattering, we are giving some energy, and you are getting energy which is larger than the input radiation in case of anti-stock Raman scattering. But inverse anti-stock Raman scattering, if you consider, in that case, you are providing some higher energy, and you are getting some lower energy at the output. Okay, so that is some kind of inverse action of the anti-stock. So that is the inverse Raman scattering. And there are two essential conditions for this. This is not that much important, but you have to remember. There are two essential requirements for this Raman scattering, inverse Raman scattering. First one is the simultaneous irradiation of the sample with a giant laser beam, because we need very high intensity here also. So here we have simultaneous irradiation of the sample with a giant laser beam. And second condition is that the strong continuum means a broad range of frequency. Okay. Strong continuum covering the stocks and anti-stocks. strong continuum covering the stock and anti-stock region. So we have to provide the incident radiation to the sample. So in if you are doing this in an experimental way, if you have a broad spectrum which is having both stock and anti-stock lines, what will happen in case of inverse Raman scattering? Suppose if you are having, I don't know how to draw that. Let's say you have a you have some normal Raman scattering here, for example. Okay. Normal Raman scattering, and you are getting some frequency which is higher than that of the incident frequency, like here. Okay, and you will be getting some frequency which is lower than the incident frequency. So, I'm just showing it separately, not to understand. Okay. All will come together, and you will be getting the same radiation. So you have some lower frequency here, and you have some most of the lines which are coming with the same frequency. That the these are the Rayleigh scattering. Okay, so this can happen, and if you send this to a sample, it will give you this inverse Raman scattering. So this has to be a giant pulse that you are using, giant laser pulse with a very high intensity. Then only you can observe this phenomenon. Okay, so that's the first condition, and second condition means strong continuum which covers all these stock and anti-stock region. So we should be able to see these stock and anti-stock lines in that particular continuum or frequency of range of frequencies. So that view inside on this sample where you can observe this inverse Raman scattering. So in that case, what will happen if you are having intensity of this line, this is as shown in this figure, and when it comes out of this sample after inverse Raman scattering, then you will be getting much higher intensity at the center, which means that more photons with the frequency h nu 0, and you will be getting some less frequencies on this. Sorry, less number of photons on this anti-stock and stock. This may not happen in a single material. You can search it for that, but maybe in one case it can be a stock line which is going to be less intense, and in some cases it may be the anti-stock lines. So this is a basic schematic diagram to understand what has happened. So this is not the exact phenomena or exact picture of the inverse Raman scattering, but this is just for understanding. So here we'll be having higher intensity for this anti-stock and similar stock lines because number of photons are larger. If number of photons are larger, means intensity will be large, which means that number of photons with the frequency h nu 0 plus nu m is larger in this case. Same as that of a stock line, number of photons will be larger in that case also for the stock frequency line. But when it is passing through another sample, which will show you this anti-stock Raman scattering, and in that case, you will be having a less intensity in the anti-stock and stock lines because some of the radiation which are so in that case we have the anti-Raman scattering happen. Sorry, inverse Raman scattering happened in both these lines, and some of those frequencies changed to h nu 0. H nu 0 plus nu m is changed to h nu 0. H nu 0 minus nu m also changed to the h nu 0. This may not happen in a single sample. As I said, this is just a representation So maybe in some cases, in some sample, only that anti-stroke line will be getting decreased by the intensity, or in some other sample, the stroke lines will be getting decreased by its intensity because of the absorption of radiation and the emission of the radiation by the sun. So this is the inverse Raman scattering basic idea. You can look for more in different resources. If you want to know. So this is a simple representation of that. That is not the exact picture. Okay, so don't take it as